Stanford University.
All right, well, welcome to lecture number 4 of Stanford CS 193P, fall of 2017. Today, we're going to continue to talk about Swift. This will be the last we talk about Swift. After this, we're pretty much going to kind of assume you know Swift, and obviously we'll be learning on the fly as you go. But starting next week, we're going to dive right into iOS, UI kit, and all that. So I'm going to do a quick demo that I postponed from Wednesday of this mutating keyword that we have to add when we make something a struct versus a class. Then we're going to talk about 2 very important topics today, protocols and closures, or functions as types in general, those 2. And in between, I'm going to talk about string, which is important in a way, but it's not the monstrous important topics like protocols and closures are. Okay? So let's dive right into that demo that I had. Remember, we were talking at the time about making things a struct, and that it's a little different than a class because of that copy on write. Swift needs to know when a function might actually modify the thing so that it knows to actually make a real copy. So let's go back here to our app, concentration, where we were. Let's go to concentration, which, if you recall, we made be a class, right? Class concentration. And this could have just as easily been a struct. I really made it a class just so when we were doing like the initializers and stuff, you could see the difference between concentration and card, because card was a struct and concentration was a class. But there's no reason concentration wouldn't have been struct. It's probably might even be better as a struct here. There's no real reason. Now, we don't pass concentration games around and all that. It just kind of sits in our controller. It's a pointer to our, not really a pointer to our model, but this would embed the model there. So it doesn't really matter too much. But when I change it to struct here, if I change this from class to struct, notice here that I get an error. Okay, and let's scroll down, and here they are. Here's the error. And this error is saying cannot assign to property. Self is immutable. Okay, why is it saying self is immutable? I'm trying to change the cards here to say that they've matched, for example. Well, self is immutable because this function right here is not marked mutable, and so it is assumed to not mutate, not change this concentration object. Okay, so of course we need choose card to change the concentration object because it's the main thing that changes the game. So all we need to do is add mutable right here. That marks, mutating, not mutable, mutating. You add that here, and that says that this is a mutating function. All the errors go away, and we're all good to go. Question?
The function right above it, why does it get this?
Okay, the question is, why does this not need it? This is a var, okay? And this var is get and set. So Swift already knows this is mutating because it's settable. Okay, if this was get only, then it wouldn't be mutating, and Swift would know that. So for vars, Swift knows. Okay, and if it's not a computed var, like look at this var, how does this one know? That's because, well, this one is read only externally, but for us it's writable. Here, anything that's a var, it assumes it's writable. If it were a let, then it would think it's not writable. So that's how you do mutating or mutable for vars, is whether they're vars or lets, or for a computer property, whether it has both get and set. Everybody got all that? Okay, so it's only funcs that we have to put that on. Yeah, question?
Why is this unique to a struct and not a class?
Yeah, so the question is, why is this unique to a struct and not a class? Why did I need to do the struct? And that's very important to understand. Very good question. Structs are value types, right? Not reference types. So structs don't live in the heap. As we pass a struct around, since it's a value type, it gets copied, constantly copied everywhere. Pass to a function, a copy is made. Put it in a var, a copy is made. Well, that would be incredibly inefficient if it actually copied the bits of this entire thing every time. So instead, Swift is smart and only actually copies the bits when you mutate it. Okay, that's called copy on write semantics. This is why structs are different, because they have that copy and write semantics. A class doesn't have that, because when you pass a class around, the class just lives once in the heap, and you're passing pointers to it around. And there could be 20 pointers to the same object. Totally different kind of model for memory. So that's why. It's because it's a value type, the copy on write stuff. That's why we care that it's mutating. All right, let's go back to our slides and talk about the first very, very important topic today, which is protocols. Okay, it's the fourth pillar of building data structures inside of Swift. You already know a lot now about class, struct, and enum. And a protocol is something where it's very simple concept. A protocol is basically just a list of methods and vars with no implementation, but it's the use of having protocols. It's so pervasively used throughout the Swift language and the runtime that makes it so powerful. So first I'm just going to go through a little bit of why we have protocols, then I'll show you the syntax of protocols, okay, what it looks like to type in a protocol and define one. Then we'll start talking about the use of protocols. Where do we use them? Why are they so valuable? Okay? So let's start with what protocols are all about. Okay? Protocols are essentially a way for callers to call an API with anything they want. Any struct, enum, class, they can pass anything they want in. And at the same time, the receiving method can specify what it really wants. So both sides get to do what they want. Okay? The receiving thing gets to say what it wants the thing you're passing in to do, and the thing passing in can pass whatever it wants as long as it does that thing. Okay? And to do all this, all a protocol is a list of vars and functions. That's all a protocol is. It's just a list of them, not an implementation of them, anything, just a list of them. Okay? And it's how we use them in the API that lets us get this behavior of having the callers and the callees get to express things the way they want. Now, what are protocols good for? They make APIs very flexible and expressive, as you're going to see. They're super good for blind structured communication, like remember back to my MVC talk, the communication between the view and the controller, all those will, did, shoulds, and the data at, count, those kind of communications between a view controller, that all had to be blind because the views are generic and the controllers are very specific, okay? And protocols is how we make that work. It's also great for mandating behavior. For example, in a dictionary is a hash table. Raise your hand if you know what a hash table is when I say that. Okay, everybody, good. So it's a hash table, so the keys of a dictionary clearly have to be hashable, right? You have to be able to get a hash value, otherwise you can't hash them and put them in as the keys of this hash table. Well, protocols let us define dictionary in a way so that we don't use any keys that aren't hashable. Okay, so mandating behavior of hashability, for example, of the key. It's great for that. It's also great for sharing functionality between very disparate types that you would never use object-oriented inheritance to make them share a base class, but they are very similar. For example, string, array, countable range. They are all collections of things. Now they're completely different. Come on, a countable range and a string are completely different. But they are both collections. A string is a collection of characters. A countable range is a collection of integers if it's a countable range of int. So they do share some, and protocols has mechanism to allow you to share that kind of similarity without having to have all those things inherit from some common base class that knows about collections of things. You see what I'm saying? And so in a way, protocols provide multiple inheritance. Now, since protocols are only doing the declaration of the vars and functions, there's no storage of those things, so there's no inheritance of data. It's purely just inheritance of functionality, okay? All right. As I go through this explanation, it's super important to understand that protocols are just a type. Just like a class is a type, a struct, an enum, a protocol is a type. A first-class type, just like all the rest of these types. That's very important to understand. All right, so let's dive into what a protocol is. There's three parts to a protocol. One, there's the declaration of the protocol, just like you have a declaration of a class or an enum of struct. For a protocol, that's just a list of methods with their arguments and return values and a list of vars. Okay? That's it. That's what a protocol is, a declaration. Second part of a protocol, though, is a class or a struct or an enum raises its hand and claims to implement those methods and vars in that protocol. So there's the claim to implement a protocol. That's the second part, because somebody has to actually implement those methods that the protocol is a list of, and that's classes, structs, and enums. So they have to claim. And then the third part is the code in those classes, structs, and in enums that actually implements the protocol methods and vars. Okay? So notice I'm mentioning vars. The vars, the storage of the vars, if they're not computed vars, has to be in some struct, enum, or class, because that's the only places you can have any storage, right? Okay, so that's it. Those are the three parts to a protocol. Now I'm going to take a little aside, and I'm not even going to spend too much time on this, but all the methods and vars in a protocol are mandatory. If you want to raise your hand and say, I implement this protocol, if you're a struct or an enum or a class, you have to implement all the methods and all the vars, okay, in Swift. However, in Objective-C, that was not true. Okay? In Objective-C, protocols could have optional methods or vars in the protocol that you could choose to implement or not. Now, that's quite a big difference, and the way that Swift deals with that is it allows you to put @objc in front of your declaration of a protocol and to make it so that this is an Objective-C protocol instead of a Swift protocol. And the only difference is that now methods inside of your protocol can be marked optional. Not optional like, you know, question mark, exclamation point, that kind of optional enum. I'm talking about optional like you can optionally implement the method you don't have to implement if you don't want to. Okay? So that's a special kind of backwards compatibility mode to Objective-C. But in Swift, we don't do that. So the only time we're ever going to have this going on in this class is when we're using iOS API that was designed back in the Objective-C world, specifically delegation, which is that blind view to controller communication. That is all Objective-C style protocols. And so when you start using that down the road in the coming weeks, you're going to see these protocols that are marked Objective-C, and some of them are marked optional, that you don't have to implement a method. That's not Swift, okay? That's Objective-C compatibility, okay? So I'm just put that in the back of your brain so that when you see it, you're like, whoa, I thought I had to implement all the methods in a protocol. Yes, you do in Swift, okay? Only this exception. All right, back to protocols. Okay, so how do we declare a protocol? What does the syntax look like? Well, it looks a lot like declaring a class, okay? Protocol, some protocol. Some protocol is the name of that protocol. Just like if you said at class whatever, that would be the name of the class. Notice that there's also colon, inherited protocol 1, inherited protocol 2. Actually, there can be any number of these. These are the other protocols that some protocol inherits. Okay, so there is inheritance in protocols. It means a little bit different thing than in a class. Okay, inheritance in the protocol world means if you want to claim to implement some protocol, you also have to implement inherited protocol 1 and inherited protocol 2. So it's almost like it's a mandatory additional protocols you must implement if you want to say you implement this protocol. We call that protocol inheritance. Okay? We call it that because some protocol inherits the requirement to implement these other protocols. Okay? Now, once you go inside the definition of the protocol, you can see there's no code. Okay? Protocols have no code. They are not implementations. They are purely declarations. And in fact, when you declare that you're going to have a var be part of your protocol, all you get to say is whether it's a read-only var, which would be get, or a read and write var, get set, like this. So this one right here, some property, would be get and set. So if you want to implement this protocol, you're a class or a struct, and you want to implement this, you would have to have a var that can be get and set. Okay, that's what that means. Any methods that you have in your protocol that might be implemented by a struct and modify the thing have to be marked mutating, of course, right? Because again, Swift needs to know, oh, this method might change the thing that implements it. Now, there's a little trick if you want. If you know this protocol is never going to be implemented by a struct, then you don't need the mutating, but you have to mark the protocol to say this is a class-only protocol. You do that by saying :class as the first thing right after the protocol declaration. See how I put that yellow :class up there? Okay, so that if you did that, then you would not have to put the mutating, because of course you never have to put mutating in a class. But then this protocol could not be implemented by a struct. It could only be implemented by a class. We rarely do this. Okay, we don't usually make a protocol be restricted to a class, and in fact 99% of all the protocols you're going to see in iOS could be implemented by anybody. Okay, what else we got here? Every clicker. Yes, you can even add an init to your protocol. And that means if you're a class or a struct that implements this protocol, you have to implement this init. So I have to be able to initialize you. Okay, so that was how we declare a protocol. Now let's look at how a class or a struct raises its hand and says, yes, I will implement this protocol. All it does is in a class, after the superclass, you just say comma, all the protocols you claim to implement. It's as simple as that. And of course, for a struct, there's no superclass, so you would just say, enum or struct, whatever, colon, the protocols you implement. Okay, so that's how you claim. This is you raising your hand and say, I implement that. As soon as you say that, the Swift compiler is going to check to make sure you actually implement those methods and vars in that protocol. And if you don't, you're going to get errors. It's going to say, you do not implement the some protocol method, whatever. Okay, and you're going to have to go do that. All right, you can do any number of protocols you want. That's sometimes why we say that protocols can provide multiple inheritance, because you can have as many of these as you want going on there. By the way, if there is an init in the protocol and you're a class and you say you implement that protocol, you have to mark the init required. That's because you wouldn't want a subclass to come along, subclass that init away, which is possible. It's possible to subclass and make it so an init doesn't work anymore from your superclass. You don't want to allow subclasses to do that, because then a subclass would no longer implement this protocol, and yet people might think it does because it inherits from something that does. So once a class implements protocol, all its subclasses have to as well, so all inits would have to be required. Because init's kind of special in that it's possible when you subclass to make it so you no longer implement a certain init with certain arguments. Okay? By the way, in your reading, there's a whole bunch about making inits in classes. It's probably the most complicated, long part of your reading for this week. You're going to have to fight through it because it's pretty complicated. Inheritance makes initialization really difficult because you've got your own vars, you've got your superclasses vars, you've got to get things initialized in the right order, all that. It's quite complicated. So unfortunately, one of the things is that your subclass can make it so you don't implement an init anymore. So that's why you have to mark it required. Okay? One thing too is you don't have to add your conformance to a protocol. You don't have to add all the methods and vars in that protocol in your actual class declaration or your struct declaration. You can add it with an extension. You know how we can extend int to add arg4random? Well, we could extend int to conform to some protocol. Okay? That would be perfectly fine. We would just say extension int colon the protocol we wanted int to implement, and then in the extension, we would put all the implementations of the vars and methods in that protocol. Okay? And this is actually quite common to use an extension just for code bookkeeping. We'll sometimes use an extension to implement a whole protocol. It's just nice, it groups it all nicely. Okay, let's see an example of using protocols like the type they are. Okay, protocols are types. So let's see, here I have a protocol called movable. Okay, it has one method in it called move2, right? And I've created a class called car, which can be moved, and another class called shape, like triangle or square, which can also be moved. Now, a car and a shape, incredibly different things, and one's a class and one's a struct, but both of them implement this same protocol. Okay, and we're going to see what it looks like in the code when you have this kind of situation. It's just perfectly legal to do this. And so I've created a couple vars down at the bottom there, a Prius, which is a car, and a square, which is a shape. All right, now I'm going to declare a var, thing to move. It's going to be of type movable. Remember I said protocols are types. So I made thing to move be of type movable, and I assigned it to Prius. Is this allowed? Can I assign Prius to thing to move? Sure, because a Prius implements the movable protocol. It implements that move2 over there, and it also claims to implement movable. So this is a perfectly legal statement right here. But this has made a variable that is not of type car, or something like that. It's of type movable. So I can send messages like thing to move dot move. That's perfectly legal, but I cannot say thing to move dot change oil. Even though a Prius is a car and a car implements change oil, do you see why I can't send that to thing to move? Because thing to move is a movable. It's not a car, it's a movable. So even the car that happens to be in that variable, it can do change oil. I can't send it. Swift will not allow me to send that message because thing to move in Swift's mind is just a movable. The only thing Swift knows that it can do is move to. Right? So this is the most important thing on this entire slide is that red thing. You cannot do change oil if you have a var, which is of type thing to move. But what are some of the things you can do? Well, I can say thing to move equals square, because a square is a shape, and a shape implements movable. I could even have an array of movable and put a Prius and a square inside of it. Okay, even though Prius and square are completely different, one's a struct, one's a class, one's a car, one's a shape, they're completely and utterly different. They can be in the same array because they're both movable. You see that? And of course, I can have functions that take movables as an argument. Here's slide, which takes a slider, which is a type movable. And inside, I can say slider, move to, position to slide to. And then I could call slide the Prius, slide the square. Perfectly legal to say because those are movables, yeah.
So does that mean that the move to functions written in car and shape have to do the exact same thing? Or do they just have to be different?
You mean do the exact same thing, like perform the same action? Right. Okay, so the question is, does this mean that move to in car and move to in shape, do they have to do exact same thing? And the answer is no, they can do anything they want. They can do whatever move to makes sense for a car or whatever move to makes sense for a shape. Okay?
And if you declare thing to move of type movable and you call move to, how does it decide which move to use?
Okay, so the question is, if I declare this movable protocol and then I say something's a movable and I call move to, how does it know which one to use? Well, because Swift underneath knows which type it is. Okay? When we say thing to move dot something, at that level we're the programmer and Swift is enforcing that it has to be a movable. But when it comes to actually executing the code, now Swift looks and says, oh, it's a car, so I'm going to use car's move to. Okay? So Swift behind the scenes is doing it. But the whole reason that we're typing thing to move to be of type thing to move is because we're telling everyone who's reading our code, I'm just using this thing as a movable thing. I don't care that it's a car. My code works on anything that's movable. So I'm just communicating to people reading my code and to myself and all that. But Swift under the covers, of course, knows which move to execute. It is possible, by the way, to have functions that take an argument that has to implement multiple protocols. So here, the slip-in slide, this function, its argument x, those things have to implement movable and they have to implement something called slippery, which is not shown on this slide. So now I cannot say slip inside Prius, because while Prius is movable, it's not slippery. And so this would not be allowed. Swift would complain here. But that's how this little ampersand, that's how you make it so it takes multiple. It requires multiple protocol conformance. Okay? So you're getting a feel for how we use a protocol by declaring vars and arguments to functions. Okay? So it's only scratching the surface of protocols. Yeah, question?
In that last slide, you had thing to move set to Prius and square.
Yeah.
And then so when you call a function
Here, let me back up. Sorry. Okay, so what was it?
So you had thing to move set to Prius first, and then you set it to square.
Yeah.
Yeah,
up here.
So when you call a method on thing to move, which one does it do it on both? Or?
Okay, so he's saying, look, I set thing to move to be a Prius. Okay, then I call move to. Which one did it do? Obviously the Prius. Then I set thing to move to be square. Now if I called move to, it would use the squares one. So it's whatever the last thing it was set to, that's what it's going to use. Question?
In car, the implementation of move doesn't have the mutating attached to it. Are you allowed to just drop that whenever relevant?
Great question. He's saying up here, look, in car, move to, no mutating. See down here in shape, we've got mutating. Up here, we've got no mutating. That's because car is a class. Classes are reference types. They don't need mutating. So it's perfectly fine. Any other questions about this? Okay, excellent. So now let's talk about the uses of protocol. Now that we kind of know what protocols are and how we can put them in our API, how do we use it? Well, a super important use is this MVC delegation thing, right? We've got these generic view things like scroll views and table views and things like that. And then we've got these very specific controller things. How does a generic thing talk to a specific thing without knowing anything about that specific thing? Because obviously when scroll view ships from Apple, it knows nothing about concentration games. So how do we do that? Well, we use protocols. Okay, it's quite simple. So this is the will, did, shoulds, and the data at. So let's take a look how we do this, all right? It's kind of 6 steps. first a view, like a scroll view or a table view, it declares its delegation protocol. That's just a protocol with a list of all the will, dids, and shoulds that it wants to send. Okay? Remember, a protocol is just a list of methods, right? So it creates that protocol. Then the view, the scroll view, it creates a var in itself, a public var. It's weak, it turns out, and so it's an optional. And that is of type that protocol. Okay? Now that's great because now the view, whenever it wants to send will, did, should, it just sends it to that var. And that works because that var is of type that protocol. So of course it can understand all the will, did, should. Then the controller comes along and says, raises its hand and says, I implement that scroll view delegate protocol by putting it on its little class line right there. And the controller sets itself as that delegate var. It literally says that delegate var equals self. So it's setting itself as the delegate. And that's legal because the controller has claimed, hey, I implement that delegate. And that delegate is of type that protocol. All's good. Okay? And then, of course, the controller has to implement all the methods in the protocol. But since this is an Objective-C protocol, it actually only has to implement the non-optional ones. Okay? And actually in delegation in iOS, almost all the methods are optional. So usually you only have to implement the one you really want. Okay? But the controller implements the method so that it successfully fills out its claim to have implemented it. And that's it. Now the view is hooked up to the controller. The view can send will, did, and should all at once. It has no idea what kind of class is doing it. All it knows about, it doesn't even know if it's a class. It could be a struct. It knows nothing about it. All it knows is that that thing implements its protocol, so it knows that it can send will, did, and should to it through that delegate var. Okay? Make sense? So let's look at the code for this with the example of a scroll view. Okay? Oh, yeah, sorry. Yeah, you find this delegation everywhere in iOS. It was designed in Objective-C world. In Swift, we have closures, which I'm going to talk about later in this lecture. And you could use closures for some of this stuff. But even with closures, delegation is a pretty cool way to do this, to have this blind communication. All right, so let's look at the example of UI scroll view. So this is what the var that the scroll view would have in itself. Okay, this is a scroll view var. It's a weak. Why is it weak, by the way? Because here the view is going to have a pointer to the controller, and we know that the controller has a lot of pointers to the view. They'd be keeping themselves in the heap. Okay, so what this view is saying here is, I want to point to whoever receives my will, dids, and shoulds, but if that will, did, and should guy wants to leave the heap, that's fine by me. Just set this to nil and I'll stop sending messages to it. Okay, so that way the view won't keep the controller in the heap. So anyway, notice it's an optional because it's weak. This is the delegate. It's of type UI scroll view delegate. This is what that protocol looks like. It's an Objective-C protocol. It's called UI scroll view delegate, and it's got all those funcs in there. Scroll view did scroll to here. Give me the view for zooming over here. It's got about 15 of them in there if you go look at the documentation. So now the controller comes along, my view controller, and it puts comma UI scroll view delegate on the end, and it's claiming I implement that protocol. Then probably in its outlet setter, we'll see an example of this today, when that scroll view gets hooked up by iOS, in the did set of that, it probably says scrollview.delegate equals self. This is a legal statement to say, because delegate, which is this thing up here, okay, is of type UI scroll view delegate, and my view controller says over here that it implemented that. So it's legal for it to set itself as the delegate. Okay, and once it does this, they're hooked up, and now the view can send will, did, said to the controller all at once. Okay, so that's delegation, probably the most obvious uses of protocols. What's another one? Okay, remember I talked about that key in the dictionary and the hashable business, right? So of course the key in the dictionary has to be hashable. How do we enforce this in our API? Well, there is a protocol called hashable. It inherits from another protocol called equatable, and that's because if you know anything about hash tables, when you hash something, it's likely to be a unique hash, but it's not guaranteed. You have to follow it up by actually using equals to see if the two things actually are equal. That's the way hashing works. So that's why hashable inherits from equatable. So if you want to be hashable, you also have to be able to check if you're equal to something else. Now this is a super simple protocol. It only has one var in it. It's a get-only var, which is the hash value. Okay, some integer that hopefully uniquely represents you. That's what this is. Now, let's look at equatable, okay, because that's another protocol that is inherited and thus required here. What does that look like? That's a very simple protocol as well. It has one function in it, one method, which is static, meaning it's on the type, like getUniqueIdentifier was in card, remember that? And its name is equals equals. In Swift, remember, names of methods can be like emoji. Okay, it's not required to be alphanumeric characters. So they chose this to be called equals equals, which is kind of cool. Okay? And the arguments are a left-hand side and a right-hand side. Notice that the type is self. This is a type method, so self is the type. So if this were implemented by int, if int were implementing equatable, self would be int. Okay, because it would be a type function on int. And so the left-hand side and the right-hand side would be ints, of course. So this is basically saying that your type has to have an equals equals method that compares two ints, or whatever you are, and sees if they're equal and returns a bool, yes or no. Okay? Now, so that's what we have to do to be hashable. But what's really cool, that the equals equals operator in Swift, okay, when you say like x equals equals y, that's actually not like built into Swift or anything. All that does is look for this method. Okay? So any class can do equals equals as long as it implements this protocol. So this protocol is required to make the hashable work, but it also makes the equals equals operator work. And we're going to see this in our concentration demo when I go to implement this. Okay? So now that we know that hashable means you can be a key in a dictionary, how is this expressed? Well, dictionary, which is a generic type, right? It's got these two types, the type of the key and the type of the value. It declares itself as dictionary key : hashable, comma, value. And that means that key can only work there if it's hashable. So this is how we use protocols to constrain these generic types. Right? Now value right there in dictionary, it doesn't have any colon anything, so value could be any type. You can put any type whatsoever as the value in a dictionary. But the key has to implement hashable. So let's go into concentration and do this very thing. What do we have in a dictionary? Well, right now we have one dictionary, it's the emoji thing. Its keys are int, ints are hashable, so we're good, and the values are the emoji. And the int is our card's identifier. Remember that card identifier? So I don't want to do that. I want my keys in my emoji dictionary to be cards. I want to look up the cards directly. I don't want any of that looking at the int thing. It's ridiculous. So if I go over here to view controller, here it is right here actually. See, here's my emoji thing, int to string. Int keys, string values. This has to be hashable. It is right now. But I don't want that. I just want to look up the cards directly. I don't want to use the identifier. I'm just going to take this identifier right on off of here. And when I do this, I'm going to get errors. And why am I going to get errors? Because card, see right here? Let's see if we can make this a little wider so you can see it, a little better. Down here. It says right here that we cannot subscript, Okay, it says cannot subscript a value int string with a card, of course. Okay, I said that the keys were ints, and here I'm trying to do it by card. So I'm just going to say, okay, that I'm going to have them be cards instead. So I'm just going to have my dictionary have keys of card, values of string. Okay, so now what do we got here? It says type card does not conform to protocol hashable. It worked. Okay, I tried to make a card be the key of my dictionary, and it says, no, card does not conform to protocol hashable. So the declaration of dictionary, which you can go look up in the documentation, it says card, the key has to be hashable, and it wasn't. So let's go make card be hashable so we won't have this error anymore. So I'm going to go over to card. Here it is. And here's card. I'm just going to say, okay, card is, if I can find the thing, hashable. Okay, so I just made card hashable. Now, of course, Swift is going to look at this and say, whoa, wait a second, errors here. Card does not conform to hashable. Card does not conform to equatable, which it doesn't because I don't implement those methods, the hash value or the equals equal thing. What's really cool in Swift, look at the fix button here. Do you want to add protocol stubs? Oh, yes, please. And look what it did. It added a stub for hashable and a stub for equatable. Now I just have to implement these. So making hash value, which has to be get only, that's easy. I'm just going to return my identifier. Okay? That's an extremely good hash for a card because it's unique for that card. And the equals equals is also really easy too. I just have to compare these two cards. Okay? I'm going to return if the left-hand side's identifier equals the right-hand side's identifier. Okay, so there we go. I've implemented hashable and equatable. So now, if I go back to my view controller, will that error be gone? Here's the error over here. So let's make Xcode recompile. And sure enough, look, no problems. It's completely fine with that. Okay? And that's because I made this hashable. Now, we can get another benefit of this. I'm going to go back to card. And I told you before, I didn't like that this identifier was public. I see no reason for it to be public. And we know we don't need it now to look in our emoji thing, so I'm just going to make it private. Okay? And let's see if that's going to work. So is private going to work? Let's build and see. Oh, no, we have some errors over here. So let's go look at them. Here's an error here. It says identifier is inaccessible due to private protection level. That's right. I made identifier private. What's it trying to do here? Oh, here I'm trying to see if two cards match, right? Does the match index? Oh, well, cards implement equatable now. So I can just go like this. Card match index equals cards index because I can compare cards directly now. They implement equatable, right? So now if we rebuild, that's gone away. So we had a huge benefit by making that equatable and hashable. We got to use it directly in our emoji thing to make that code look nice, and look how nice this code looks compared to how it used to look with that identifier, right? So we cleaned up our code on the use side, and we were able to go back to card and make something that really didn't need to be public, completely private. Pretty cool with that? Okay, so you're starting to see the power of protocols a-building here. So let's go back and look at even more protocol stuff that's cool. All right, here's the demo. Okay, let's talk a little bit about this multiple inheritance kind of trick. Consider countable range. Remember countable range, 0, ... less than something, creates this countable range of ints from 0 to that thing minus 1, okay? Countable range implements a lot of protocols. If you go look at countable range, it implements, I don't know, probably 12 or 15 different protocols. Well, two of the most interesting ones it implements are sequence, which makes sense, right? A countable range is a sequence of numbers from 0 to something else. And also collection, because a countable range is also a collection of things. If it's a countable range of int, it's a collection of ints or whatever. And so these two protocols define a lot of fun things, like sequence defines really only one method, next, which goes to the next thing in the sequence. But that lets you do for in. Anything that implements the sequence protocol can do for in. Okay, just like anything that's hashable can be a key in a dictionary. And then collection has even more methods. All the indexing, subscripts, all that stuff is all in the collection protocol. Now, why do we do this? Why do we have countable range implement all these protocols? Well, because array implements all those as well. And so does dictionary and set and string. All these classes that are sequences of things or collections of things implement all these exact same things. And so I, as a programmer, only have to learn these things once. Okay? I only have to learn for in once. And all I need to know is that the thing I want to for in over has to be a sequence. So I can just look to see, does this thing implement that protocol? Or I could even invent my own things that I could for in over. All I have to do is implement the sequence protocol, which really only has one method in it, ultimately. So that's one good reason why, because I learn indexing, index of to get things, and I can now do index of on a string and find a character in a string, or I can do index of in an array and find the thing there. I could even do index of on a countable range, not super valuable, but if the countable range wasn't of int, then it might be interesting to do index of to try and find something where it is in the range, okay? But there's a bigger and better reason why we do this. And that's because there's a little bit of magic, or not magic, but really good design implementation in Swift, which is that for protocols, it is possible to provide default implementations of methods, okay? Default implementations of methods. So this makes it possible for us to implement index of for all of these classes in one place. So that's why, again, we think it's like multiple inheritance, because they're actually going to inherit implementation. So where do you put this implementation? Because we know protocol is just a declaration of methods with no implementation. Well, the answer is you put them in an extension to your protocol. You know how we can have extension int? You can also do extension protocol. Okay? And in that extension, you can implement as many of the protocol methods as you want. Now, you're a little bit restricted there because extensions can't have any storage. We know that, right? No var, so that's certainly a restriction. Also, in the extension, really the only methods you can use to implement it are the methods in the protocol or in a protocol you inherit. So like collection happens to inherit from sequence, so a lot of the collection methods can be implemented using the sequence by just going through the whole sequence of the collection and finding things or whatever. So if you look here, sequence has that one important method, next, which goes to the next thing in the sequence. But sequence also has all these other methods. Contains, which finds whether something's in the sequence. For each, which kind of does what for in does. Joined by separator, which takes all the things in the sequence, converts it to a string, and creates a big string joined by a separator, like comma or space. It has min, find me the minimum thing in this sequence. Max, the maximum thing. Even has functions that take closures, which I'm going to talk about soon, like filter and map, that do major operations on the sequence. Well, all the implementation of all those things, contains, for each, joined, min, max, all those things, those are all implemented in an extension to sequence that Apple provides, so that if you want to have a sequence, as long as you implement that next thing to go to the next thing in the sequence, you get implementations of all those other things for free. And that also means that array and set and dictionary and countable range are all sharing the implementations of min and max and all these things. Now, these are only default implementations. If in array you actually implement min or max or something like that, maybe you can do it more efficiently than the default implementation or whatever, you can do it, okay? But it replaces the default implementation that's in the extension. Okay, but are you getting the feel for what I'm saying, why this is valuable to have these default implementations? You can have these really powerful protocols, and you only have to implement one of the methods, and you get implementations for all of them. And then they're shared across all these weird different classes, like array, string, countable range. They all get all these implementations. They don't have to implement any of that, and they get it for free. Okay? Now, all of this that I'm talking about, generics, value typing, var versus let, immutability control, constraining things by protocols, extensions of protocols, all these things add up to support a kind of programming called functional programming. How many people here have heard about functional programming? About half of you, see. So I encourage you at your Stanford careers, go take a class and learn about functional programming. It's really kind of the evolution, some would say, of object-oriented programming. Okay? It's a little different way of thinking about dividing things up. It allows you to get things like multiple inheritance without things getting completely out of control. Since things aren't living in the heap, you don't have 20 pointers to something and you're not sure who's going to modify things, so your programs are much more provable, right? You can prove that they do what they do. You don't have to worry about what pointers are messing this thing up in the heap. A lot of advantages of it. Now, what's really cool about Swift, it supports both these programming models. Object-oriented programming, which is all I'm going to use in this class because that's the prerequisite for this class, and functional programming, which is what pretty much all of the foundation of, the foundation framework, like dictionary, array, string, all those things, those are all built with a functional programming model. Okay? Swift supports them both equally, which is really great. So it's kind of the best, it's a mix between languages like Haskell. How many people have heard the language Haskell? Okay, same people who know about functional programming, right? So Haskell, which is a purely functional programming language, and like Java, which is a purely object-oriented language. It's good. It's a mix of two. Okay? That's all I'm going to say about functional programming, just so that you know it's there. Okay, that's it for protocols. Okay, when you see it all in action, it'll all make a lot more sense. Hopefully it makes a lot of sense. Now, protocols are very simple, just those lists, but we can use them in powerful ways. All right, now let's go talk briefly about something that's not super important, but strings are in almost every app. And I just want to talk a little bit about how we index into strings, because it's not what you would think it is at first glance. Okay? In addition to string, the struct string, there's another struct in Foundation called character. Okay? Now a character is what we humans would perceive of as a character, okay, on the screen or whatever. However, a string is not a sequence, a string is not underlying built with characters, it's built with unicodes. Okay, unicodes are just little bite-sized chunks that can represent pretty much any language on Earth. Okay, it's international. Like ASCII, we used to have ASCII, can only really do English. Unicodes can do all the languages on Earth. Okay, so that's what's in a string. So we have a little bit of trying to bridge the world between unicodes and characters. So let me show you by example here. If we had the word cafe, C-A-F-E-X-N-T-U, right? That we perceive to have 4 characters, the C, the A, the F, and the E with the accent on it. But it might be represented by 5 unicodes, because there's a unicode which is put an accent on the previous character. Okay? So it could have 5 unicodes. Well, so how do we deal with this? Well, the main problem or the main ramification of this is that string cannot be indexed by int. Because if we had a phrase cafe pesto right there, one of my favorite pizza joints in Hawaii, cafe pesto, the P, is that at index 5 or is that at index 6? It depends on whether that E is an E with an accent or 2 Unicode characters, the E and the accent, okay? So, what are we going to do here? So, what we do is we don't index strings by int. Instead, strings are indexed by their own special type, string.index, okay? And that's the only way to use subscripting on a string. You need a string.index, not an int. So this makes people don't like this. They want to index strings by int, and I understand why, but you can't do that. So what does that mean? Well, we have to get an index. So how do we get an index? Well, you can get the start index of a string. You can get the end index of a string. You can also use index of a character to find the first index of that character. So there's a bunch of different methods and vars on string to get an index. Once you have an index in your hand, now you can offset that index by an int. So if you want to get the 4th character in a string, you have to get the start index and then offset it by 3 to get to the 4th index, from the 1st to the 4th. Okay? So let's look at the code that makes that work. So here's my pizza joint, cafe pesto here. I'm going to get the index of the first character by saying pizza joint.startIndex. That's not an int. It's of type string.index. Okay? Now I'm going to get the 4th character by taking the first character and offsetting it by 3. Now I've got the index of the 4th character. Now I'm going to get the actual 4th character by using subscripting. Okay? Pizza joint, subscript, 4th character index of subtype string.index, not of type int. And I could also do with index of. So here I'm going to say the first space character in cafe pesto is pizza joint index of space. Now the reason I have to say if let there is, of course, index of space could return nil. There might not be any spaces in pizza joint. There happens to be, but there might not be. So it would return nil then. So I'm doing if let. Now I've got the index of that space. Now I'm going to get the index to the start of the second word, the word pesto there. I'm going to do it by indexing that first space over by 1. Okay, I'm going to assume there's 1 space between words. Go to the next one. And now I'm going to get the whole word pesto by indexing string with a range. Okay, the index of a string doesn't have to be an individual index. It could be a range of indexes. Now you'll notice to make a range, I'm using exactly the same dot less than thing that I did when I made that countable range of ints. Okay, ranges are generic types. They don't have to be of ints. They could be a range of string.index, perfectly legal. Okay, and so we saw before we had a range, countable range of double precision floating points. Remember that at the beginning of the last lecture. So range is generic type. Okay, so it is perfectly legal to use a range inside subscripting, and that's true anywhere there's subscripting of collections. Okay, these methods, by the way, these index, offset, by, those are not methods in string. Those are methods in collection. Okay, the collection protocol. String may or may not implement it itself. It's up to string. The collection protocol is also generic, and so the index you use in a collection is configurable. Okay, for a string, it's a string.index. By the way, another way to get the second word, and probably what we would use, is a more complicated method like components separated by. So component separated by is a collection method. You give it an element that would be in that collection, and it will create an array with all the things, all the elements in the array grouped and separated by that thing. Okay? So this would give you an array of all the words separated by space. And then I would grab index 1, which would be the second word. Okay? So I'm showing you how to do the indexing directly, but a lot of times we use much higher level things in string. All right? Okay, so string, like I say, is a collection of character, just like an array is a collection of arbitrary things. A countable range of ints is a collection of ints. And so all that stuff is coming from collection. And collection is a sequence, we know. So of course you can do for C in S, if S is a string, C will be a type character, and you can iterate with a for loop through all the characters. There's also a really cool initializer for array that takes a sequence as the argument. So you can say array of any sequence, and what it'll do is go through that sequence and take each element and put it into the array. So it creates a big array for you because it's an array initializer, and in the array will be all the elements of the sequence. So since a string is a sequence of characters, if you say array of string, you'll get an array of its characters. And now you can use int to index them if you want. So sometimes people, they get tired of all this string index stuff. They just create an array of the characters, and then now they can use ints to get at the various characters. Okay? That's kind of a trick as well. Remember that a string is a value type. It's a struct. We almost always use immutable strings, like let s equal something. We're working with it immutably. But of course, there are mutable versions, mutable methods. There's another kind of protocol called range replaceable collection. That's kind of a collections that can be mutated. Ranges of the things can be replaced. And so here's a method in that. Insert the contents of a collection of characters, which string is, at an index. So in this case, it's index of space. That's got to be a string.index right there. And so I can insert the word foo into Cafe Pesto. Okay? So you can do this. We don't do this that much. We tend to just use them immutably, and we use plus to add them together and stuff like that. Okay? So that's string. It's that little weirdness about the indexing. Now, there are lots of other methods in string. I wanted to show you an interesting thing about one of them. So here's replace range, which my pointer doesn't work anymore. But if you look at replace range, you see where it's red right there? That's that ... less than thing. Look, I forgot to put something on the left. So what does that range go from? Okay, we know it goes to s.endIndex. Well, Swift is smart enough to know that that is a range of this string's indexes, so it'll automatically put start index at the beginning. Okay? And if you left off the other side, it would automatically put end index at the end. Okay, so you can leave those range things open-ended, but Swift has to be able to infer the type of what's going on there. So you can't always do it, but in that case you could. Okay, so that's string. I guess we'll go like this. So to make this all understandable, let's go back to our concentration, and we're going to make this thing right here, this emoji choices, which is currently an array of emoji strings. I'm going to change that. I'm going to copy and paste it here. I'm going to change it from being an array to being a string. Okay, so I'm going to take off the array things, and I'm going to get rid of all of these little commas. And now emoji choices is going to be a string, and I'm going to have my code be the same, but instead of grabbing it out of the array, it's going to grab it out of the string. Now, as soon as I change that to a string, look what happens. Cannot convert value of type int to expected argument string.index. Okay, remove at right here, which we moved to remove the thing. Where do you think that's declared? Anyone want to guess? Is that an array thing? String? No, that's in collection, range replaceable collection, right? So it's in a protocol somewhere that both string and array implement. So you would think it should just work here. Because emoji choices, yeah, now it's a string, but remove at is in range replaceable collection. They're both range replaceable collection. Why doesn't this work? Well, because strings are not indexed by ints. And so this doesn't work. So we have to create a string.index. So I'm going to do that. I'm going to create a random string index. And I'm going to do it by using that index offset by thing. So I'm going to say emoji choices. Give me an index. I'm going to use this first one right here, index offset by, which lets us take a known index and offset it by something else. The known index I'm going to start with is the start index of this thing. So emoji choices.start index. And I'm going to offset by a random int. So that offset, that can be by an int. Okay? That happens to be because this particular collection strides, or the distance between indexes, is an int, even though the indexes themselves are string.index. So I do that. So now I'm going to put random string index in here, and all should be well, right? Because remove at, oh no, still doesn't work. What's this error? Cannot assign value of type character to string. Okay, this is a dictionary that's looking for strings. Okay, why is this a character? Well, because a string is a collection of character. So if I remove at, I'm removing a character. So no problem here. We know that we can probably convert types, and we're going to do that by using a string initializer that takes a character as an argument and returns a string with just that character in it. So now we converted it. Okay? So that's it. That's all we need to do. And I did this just so you could see all that offset by and all that stuff, so you could see how we would index this into a string instead of doing here. And so hopefully this is still working. Yes, it is still working. Okay? Got it? Everybody questions about this? So this is the important line of code in here. And also a little bit of understanding that even though remove at is in collection, range replaceable collection, the types matter because it's a generic type. Okay, collection is a generically typed protocol. All right, let's go back. Oops, not there. Here? No. Here. All right, let's talk about another class that has to do with strings, which is NSAttributedString. So NSAttributedString is a string that every character has a little dictionary associated with it, and that dictionary can have lots of little keys and values that say how to draw that character on screen. Okay, so those dictionaries can have things like font, color, all these things. Okay, that's what an attributed string is, right? A string with attributes of each character, right? The dictionary that each character can have, the keys are well known. You can look them up in the documentation. The values depend on the type, okay, of things. So sometimes the values are UI font, which is a font thing. Sometimes the values are colors. Sometimes they're floating point numbers, etc. Now, a lot of times we use the same dictionary for big, long ranges of characters, right? Like if users select some text on screen and they say make it orange, that we're going to have one dictionary for all those characters. So it's not like every character has to have a different dictionary. And in your homework, the entire string is going to have one dictionary. So I've given you a really easy use of attributed string, and you're going to see why I did that in a moment here. Once you have an attributed string with all those font and color for each character, now you can use it to set the text in a UI label, or to set the title of a UI button. Or next week, we're going to learn how to draw it directly on screen in our own drawing classes. Okay? Here's how you create and use an attributed string. And it's got red. Anytime you see red on my slides, it's kind of like, oh, look out, okay? And this is red because it's really weird, okay? And why is this really weird? Well, it's really weird because this is an Objective-C API that's trying to live in the Swift world. And that requires a little bit of a compromise. There's not a lot of APIs like this. Every time iOS comes out, the next one, I always hope they're going to have non-NS attributed string, just regular attributed string where they'll fix this. But they haven't done it yet. So when you're declaring those attributes, the little dictionary that goes on each character, you have to give it an explicit type. You cannot let the type be inferred. And that's because those values could be fonts, colors, whatever. So Swift can't infer what the value of the dictionary is. So the type that you're going to use here is keys are NSAttributedString key. And you can just look that up in the documentation, see what the choices are. It's things like font, underline, strike through, all the things you would think could be. And then the value is any. Okay? So any is a special Swift thing that means anything can go here. Any struct, any class, any type. So this is very non-Swift because Swift is strongly typed. And here there's no type. Okay? So you would never have an API like this in Swift. Okay, if this weren't an Objective-C API brought forward to Swift, you would never have this. Can anyone think of what we would have instead of any right there? What type of thing instead of any? How about an enum with associated values, right? If you had an enum and one of the enum things is the font, then the associated value could be a font. Or what if the thing was the color of the text? Then the associated value could be a UI color. You see how we would do that in Swift? Well, we didn't have those enums when Objective-C did this, so we're stuck with any. Okay? Never use any in your data structures. Any is purely so we can deal with these old Objective-C things, okay? All right, so now that I've declared the type to be a dictionary with NSAttributedString keys and any as the value, then I can make my dictionary. And so stroke color is obviously the color that it strokes the outside of the text. There's also foreground color, which is the color it puts the inside of the text, the fill color. There's also background color, which is like if you had a highlighter, that's the background of it. There's also stroke width. Stroke width, if it's a positive number, it outlines. Okay, if it's a negative number, it's solid. The character is solid. Okay, you'll see that. We're going to do a demo of that. Okay, so you can do this. You can put these things in here. For your homework, you'll use stroke color, stroke width, maybe a couple others. In the hints, I kind of tell you the things you need to use, so I don't want you wasting too much time looking up all these things. Then you can create an attributed string with that dictionary for all the characters in the string by just saying NSAttributedString using the initializer that takes a string and the attributes. Okay, so that creates an attributed string. Then I can take that attributed string and like put it on my flip count label, right? Now my flip count table. So this particular one, since I'm using a positive stroke width, this would be outline text on my flip count. So we're going to do a demo and see what that looks like in a second here. I just briefly want to talk about the peculiarities of NSAttributedString since there's an NS. You know, you see that NS at the beginning and you know, this is kind of an older API. It's not a string, okay? It's a totally different thing. Okay, NSAttributedString is a class. It's completely different than string. It works completely differently. Because it's a class, not a struct, you can't make a mutable one by just using var. You have to actually use a different class, NSMutable attributable string. If you actually wanted to go set the dictionaries on certain characters individually, you would need to use a mutable attributable string, a completely different class there. Also, NSAttributedString was built and constructed internally with NSString in mind. NSString is the old Objective-C string. NSString and string have a little different Unicode encoding underneath. So when you have wacky characters like emoji or cafe in there, the indexes into them might not quite match up, okay? And there's automatic bridging between string and NSString. So if you have any iOS API that takes an NSString as an argument, you can just pass a string. It just automatically works, except that this little encoding doesn't always get fixed up quite right. So the bottom line here is if you are going to be trying to index into an NSAttributedString and you have wacky characters like emoji or cafe, the indexes might not line up very well. Okay? Now in your homework, you don't have to worry about any of that because I'm only going to ask you to make the entire string have the attributes. So you're not even doing any indexing into there. But in the future, if you're ever using attributed string, just be careful about the indexing in there if you got wacky characters. Okay? All right, the demo. So I'm going to do this flip count thing and show you what this looks like real quick here. Where do we do that? That's right up here, right? Here's where we set our flip count label to flip count. So I'm going to put attributed text there. So I'm going to let my attributes, which I have to type to be NSAttributedString key, and then any, okay, equals. And now I can just put the things I want. So I want the stroke width to be 5.0. Okay, that's a fairly thick stroking width. And then what was the other thing I said I wanted to do? Oh, the color. So the stroke color. And I'll go ahead and use a color literal here. Use our favorite color, which is orange, Halloween color. Okay, so now if I want to use these attributes to draw the text on my label, I'm just going to create an attributed string. So I'm going to say let attributed string equal by creating an attributed string with its constructor. I want the one down here at the bottom that takes attributes and string. Okay, this is what you're going to do for your homework too. I put the string, it's just this string right here. And the attributes is these attributes I just created up there. And then instead of saying flip count label subtext, I say attributed text. And for a button, you would say set attributed title for state instead of set title for state. And that equals this attributed string. Okay, so that's all I need to do. So let's run this, and we're going to see something a little bit kind of odd about this, though. Okay, a little bit unexpected, I think. So here we go. Hey, it didn't draw anything different. Look at that, flips 0. That looks exactly like before we made this change. But, oh, look, if I click, now I'm getting the outlined font. See how it's outlining my flips? So why, when it first came up, didn't this work right here? Yeah, because this right here, this little equals 0, this initialization, that does not cause the did set to happen. Okay, so that's an important thing to know. When you initialize a var, it does not invoke the did set. Only later settings of flip count. So how can we fix this? Well, I'm going to take this and put it in its own little func. Okay, private func. I'm going to call it update flip count label. Okay, I'm going to put that in there, and I'm going to call this update flip count label in here. Update flip count label. And where's the other place I need to update the flip count label? Well, here's another thing to learn. It's kind of cool. This right here is the label, right? If you remember in our UI over here, that this right here is connected up to that, right? It's connected. Now, this connection gets made by iOS when you start up your UI, right? It makes that connection. Well, when it makes that connection, it's setting this. So guess what? We can use did set here. Okay? When you have an outlet, did set does get called when that outlet gets set by iOS. When this connection right here gets made, that gets called. So here we can update our flip count label here. Okay, so now that flip count label is going to be updated when we first connect that flip 0 and also every time we change it after that. Okay, got it? All right, back to our slide. So you learned two things there, right? You learned that the equals 0 didn't cause did set to happen, and you learned that on an outlet you can set things because that outlet just got hooked up for you. All right. Last really, really important thing here, we're going to really rush because we're running out of time. This is very important. This is about functions as types. So I believe the Supreme Court ruled a couple years ago that functions are people too, okay? And so functions get the full treatment of a type that any other type gets. You can use a function as a type anywhere, all right? And you do it just by declaring an argument to a function or a var, whatever, to be of type function, and you specify the arguments and the return value of that function, so it'll be a variable of that. So you can do this anywhere a type is allowed. Let's look at an example. I have a var here called operation. It is of type function that takes a double and returns a double. So the syntax here is awesome. It looks just like declaring a function that takes a double and returns a double, just no names of arguments, but the types are all in there. Okay, so this is how you declare a function. Okay, you declare a var that is a function. You can do it for variables, passed into functions, parameters, everything. Okay, you can always do this. So you can assign this var exactly like you would think. I'm going to assign operation equal to square root. Okay, square root is a function that takes a double and returns a double. So it's perfectly legal for me to say operation equals square root. Right? And how do I call it? Well, I call it just like a function. Operation of 4.0 is going to call, in this case, square root of 4.0 because operation is a function, var that's holding a function in it, and that function is square root. Okay? Could not be simpler. Everybody cool with this? Now, other languages have function pointers and all this stuff, but it's all pretty tortuous to use. But in Swift, it's a first-class citizen. Okay? Functions are a first-class citizen. They will be the argument to many iOS methods. Functions will be. Okay? Now, a lot of times, the function you want to pass doesn't already exist, so it forces you to go write a function to pass in. For example, let's say I had the function change sign. Okay? So there's no thing like square root that does change sign. So I have to write a really simple little function here, change sign, and all it does, it takes a double and returns a double, just like square root, and it returns minus the operand. Right? So I'm changing the sign of the operand here. So I could use it in the same way. I've got operation, I'll say operation equals change sign instead of operation equals square root. But this is kind of a lot of typing and an annoyance to have to go create a whole function to do change sign when all I want is for that thing to change sign. So we can use what's called a closure. How many people have heard the phrase closure, know what a closure is? Okay, about half of you again. Okay, so closure is really like an inline function. It's a little special in that it captures the state around it, but it's essentially an inline function. So what does the syntax look like if we wanted to take change sign and just drop it right into the middle here instead of having a separate function? Okay, how would we do that? All right, we're just going to pick up all of change sign except for its name and move it down. Watch. Okay, so I just put it right in there. Now I do have to make one syntactic change here, very important. I have to move that first curly brace, the one right before the word return. I have to move it to the beginning and replace it with the word in. So watch this happen. Okay, this moves to the front, put the word in. That's it though. Once you make that small syntactic change, you can drop any function right in there. But it gets much better than this because we have type inference in Swift. And Swift can absolutely go to town here because it knows a lot about what's going on here. For example, Swift knows that this operation thing returns a double. It knows that. So you don't need to say returns double there. So just take that out. It also knows that the operand is a double. Okay? So you don't need to say that that operand is a double. You can take that out. Right? It also knows that this function returns something, so you don't need the keyword return minus operand there, so we can take that out as well. Okay? And even more, Swift knows you want to have these embedded functions all the time, and it's a little annoying to have to think up a name for the argument to this thing, okay, that operand word that I had to think up there. So it lets you substitute $0 for the first one, $1 for the second, $3 for the third one, okay? So I'm going to replace operand there with $0. And when I do that, I don't need the in anymore either. Now you see the power of the closure. Okay, I wanted to have an operation that changes the sign, and I barely had to type any more characters than the change sign, just the curly braces around it. Okay? And that's still going to do, operation 4.0 is still going to do minus 4.0. Okay, so you're going to be using closures all the time, and you're going to be using these $0, $1, $1, $2 as the argument names. And it's going to make it so that you have to type very little code to put the things in. Now, why do I want closures? Why do I want functions as arguments? Well, it's usually because you're passing something to a function that wants to know what to do. Okay, a function is a great way to tell it what to do. Now, why might it want to know what to do? Well, maybe it wants to know what to do if there's an error. Okay, I'm going to do something, it might generate an error, and I want to call a function in case there's an error so you can handle this function. Maybe it wants to know what to do if it's going to do something that takes a long time. It's going to go on the network and download something off in the background, and when it's done, it wants to tell you. Okay, call a function to do that. Another thing is it might be doing something repeatedly. It wants to do the same thing over and over, so it's asking you to tell it what to do over and over. So let's take a look at an example of that last one there, doing something over and over. So array, and actually it's a collection. And anyway, array has a method called map. And what map does, it takes only one argument, a function, and it applies that function to every element in the array and creates a new array. Okay? So map returns in a new array where every element in the array you send it to gets operated on by some function. In other words, it's a way to pass a function into an array and tell it to do it on every element. Okay? That's what map does. So how does that work? Here I have an array of floating point numbers. They happen to be the first 5 prime numbers, right? 2, 3, 5, 7, 11 here. And what if I wanted to have an array of all -2, -3? Well, I would just say negative primes equals prime.map. The only argument is a function that does change sign, right? Just like we had in the previous slide, change sign. And now I get a new array. Negative primes is going to be a new array with -2, -3, -5. You see how I used map there? Now, what's another example? Maybe inverting the primes. So I'm going to provide a closure, 1.0 divided by $0. Now I get 0.5, 0.33. Maybe I even want to convert it to a string. Perfectly legal. It doesn't have to be the same type. I can return an array of string. Okay? Now, Notice the yellow things up there have changed a little with each line. You see? The first one, map parentheses, the closure. The next one, map open parentheses, close parentheses, then the closure. And the third one, map no parentheses and the closure. Okay, this is using what's called trailing closure syntax. Okay, we almost always use this. The rule here is if the last argument to any function is a closure, you can move the closure outside the parentheses of the arguments. Okay, so see in the second line, inverted primes, how I moved the closure outside. And furthermore, if it's the only argument, then you can just get rid of the parentheses entirely. That's the third line. Okay? And this is just to make our code look nice, so we don't have extraneous parentheses in there that we don't. Because we've got the curly braces, so we kind of don't need those parentheses. Okay? So you'll see that in iOS, when an argument to a function is a function, it'll usually be the last argument, so that you can move it outside if you want. It's optional, you don't have to. All three of those are perfectly valid syntax right there. Okay, another cool use of closures, property initialization. What if you have a property and you want to initialize it to something, but it's not, like you just can't do a one-line thing, right? You can't say equals 5 or equals something simple. You need to do 2 or 3 lines of code to get it initialized. No problem. You're allowed to set the property equal to executing a closure. Now that closure is automatically going to be a closure that takes no arguments and returns the right type to initialize that property. So you can do anything you want in that closure and just return something of the right type. And then you execute it right away with open parentheses, close parentheses. See how there's the little open parentheses, close parentheses there right at the end of the closure? That's just going to execute that closure right there. This is especially cool with lazy properties because it means this closure won't be executed until someone asks for this property. Okay? So you're combining lazy and the closures. So closures, really cool for initializing properties. Now, one thing about closures to be careful of. They do capture their surrounding variables. So if I have a closure, it's just a function embedded right in my code. If there are local variables or instance variables in the class I'm in or whatever, and I use them in the closure, it works. Okay? And even if that closure sticks around, those things still continue to work until the closure goes away. What this means, though, since closures are types and they can put in arrays and dictionaries, closures are reference types. There's only 2 reference types in Swift, classes and closures. So what does that mean? It means this closure gets put in the heap if you put it in an array. So that array actually has pointers to this closure. Okay? Now this is a little mind-bending. I don't expect you to get this right at the top. But it also means that if you capture variables in your closure from your surrounding code, they have to go live in the heap too. Because we can't have this closure not function, right? This function has to be a function that executes, okay? So here's an example of that. Here I have a local variable called LTUAE, life, the universe, and everything, I think that stands for. It's set to 42. Okay? And my operation, the closure there, says LTUAE times $0. So that closure is actually using a local variable inside it. Now what happens if I put that operation in an array? Okay? And then later go back and get it out of the array and execute it. Well, when it does that, LTUAE still needs to be there because otherwise the closure won't execute. Okay? So LTUAE gets captured into the heap and stays there until the closure goes away. Now, this is awesome. It all just works magically. You don't have to think about it except in one case, and that's a memory cycle. This can create a memory cycle because you might capture the class that array of operations is in. Okay? If you capture the class that array of operations in, then this closure has captured that class into the heap, and that class, through its array, is captured the closure in the heap. So they're pointing to each other through the array. You see? They're creating a memory cycle. That closure is keeping the class is keeping the closure. They're staying in the heap. They can never leave until someone removes that closure from this array, for example. So we can break closure cycles like this. We use that thing I talked about last time, unowned. Remember unowned when we talked about weak and strong and unowned? And I said, oh, I'll tell you what unowned is. So I'm going to put these 2 things together, unowned and the fact that we can have these cycles. In a couple weeks, I'll talk to you how we break these cycles. Okay, how we can create a closure that will not keep something else in. Okay, So let's see a demo of closures. I'm going to improve the method index of the one and only face card to be way better. And not only am I going to use closures, I'm going to go back and use extensions to protocols and kind of tie this all together. Okay, so let's do that. Over here, if we remember we'll make one big window here. If we go back to our concentration, right, here's concentration. Remember we had index of one and only face card, which supposedly made our code simpler, which it did down here. I mean, they made this code really beautiful and readable down here, but it actually added quite a bit of code here, okay? But this is way more code than you actually need to find the index of the one and only face card if you use a method that takes a closure. Now, the method we're going to use, it's kind of like map. It's on collection. It's called filter. So what filter does is it goes through every item in the collection and executes a function that you provide. Filter only has one argument. It's a function. That function returns a bool. So it executes that function with the argument being each item in the collection. If that function returns true, then it puts it in a new array. Okay? And if it turns false, it doesn't. So it essentially filters the collection into an array, but only the ones that return true from the function. See what I'm saying? So that's why it's called filter. Filters the collection, makes an array out of the ones that return true. Well, that's great for this because index of one and only face card. How about I go look at all the indexes of the cards and just find the indexes that have face-up cards. So I just need a function that says whether a card's face up, and I can do it. So let's do that. I'm going to let index, we'll say let the face-up card indices, I'll call it. Okay, this is going to be an array. I'm going to let it equal my card indices. Okay, card indices, what type is card indices? Does anyone remember? Oh, I just showed you what it was. There. It's a countable range of int. Okay, it's the indexes into the cards array. So I'm going to filter those indices, okay, by providing a function. And it's the only argument, so I don't need any parentheses or anything. I'm just going to put it after. This function just needs to look at the index and see if that's a face-up card. So that's cards sub the index. We'll just use $0, which is the one argument of function, is face up. Okay? So that's a Boolean function right here. This is a Boolean function executed by a closure right in there that returns true if the card at that index is face up. So now I've created this, which is an array. It's an array of array indexes, by the way. Let's take a look. See? Array of array indexes. This type array index, remember we had string.index. Array.index is type aliased or just set equal to be int. That's why arrays can be indexed by int, because their array.index is int. That's not true for strings. String.index, unfortunately, is not int. Okay? So this is an array of all the indices. Now, if this only has one thing in it, then we have one face-up card. We all agree with that? So I'm just going to return here that if face-up card indices .count equals 1, I'm going to return the face-up card indices .first. First is just a collection method that returns the first thing in the collection. Otherwise, I'm going to return nil, because we either have 0 face-up cards or we have more than 1. In either case, we'll return 0. So I don't need any of this stuff right here. Okay, so this a lot cleaner than this whole thing. Everybody agreeing with that? And a little more readable too. Give me all the face card indices by filtering the indices to show me the ones that are face up. Okay, it kind of reads a little better as well. But we can do better than this even. And we're going to do better by creating an extension to a protocol down here. Okay, the protocol we're going to extend is collection. Okay, so we're going to add a var. Could be a function, but it's going to be a var, to collection. So I'm going to be adding it to string, dictionary, array, all these things. And what it's going to do, it's going to be the one and only. Okay? And it's going to return the one and only thing in that collection, if there's only one thing in the collection, or it's going to return nil. Now, what is the type of one and only going to be? Well, collection is a generic type, and it has one of its generic things is element, which is the type of the thing in there. So element is just like a placeholder, right? Like an array of element. You know, you recognize that. For in a generic type, it's the type. And of course, I want it to be optional because I'm only going to return non-nil if there's one and only one thing in this collection, this string or this array or this dictionary or this countable range. And here's how I can implement it. Watch this. Return count equals 1, question mark, first, colon, nil. Now, how am I able to do this? Well, count is a collection method. Tells how many things in there. First is a collection method. It tells how many things are, it returns the first thing in there. Okay? So since these are collection methods, I can use them in the implementation of a collection var. Okay? Seeing the power here of these extensions on protocols? And now, strings, arrays, countable ranges, they all implement one and only. So I can go back up here and just return. This is, remember, is an array of the indices of the face-up cards, dot one and only. Okay, and I don't even need this. Okay, even simpler. By the way, I could absolutely do let ch equal hello dot one and only. Okay, now that would return what? What would ch be equal to there? Anybody? It would be nil, because one and only returns if there's one and only one element, and this string has 5 elements. Okay? If I did this, what would this return? This would return h, the one and only thing in that string. Okay? So I got that by extending collection, which string and array happen to be. Okay? What's the type of this, by the way? ch, what do you think its type is? It's an optional character, okay? Optional character because the elements of a string are characters, and a string is a collection of characters. But if I click on it, it's going to say it's a string.element. So just like array.index is type alias to be int, string.element is type alias to be character. Okay, so you have to look in the documentation to see that, or you just have to know it. But if you're doing your alt clicking, I don't want you to be surprised when you see that's not a character. Okay? All right, so a lot of things went on in just this short demo here. We used the closure right here, and we also extended a protocol right here to create this method here. So hopefully you understand both of those. If you don't, use Piazza, come up and ask me afterwards or whatever. All right? See you next time. Oh, wait, sorry, one thing. Let me go back and just show you the coming up, because there is one thing to note here about the coming up, which is that Friday we were going to have the optional section, object persistence. We're not going to do that this Friday. We'll do it in a future Friday. We will do object persistence, but in a future Friday. So there's no Friday section at all this week. Next week I will be doing views, gestures, multi-touch, multiple MVCs, all that.
For more, please visit us at stanford.edu.